The switches are not considered safety-rated equipment. Safety-rated equipment is engineered to meet specific safety standards and requirements, such as those defined by the International Electrotechnical Commission, commonly referred to as IEC. These standards outline criteria for the design, construction, and performance of safety-related components and systems, emphasizing their resilience to fault conditions and reliability in critical safety applications. The described switches, rated at 10 amps and 600 volts, indicate their capacity for handling current and voltage. However, they often lack the specialized safety features and certifications necessary for equipment designated as safety-rated. Safety-rated switches incorporate several key features. Firstly, positive break contacts are utilized to ensure the reliable interruption of the circuit. Secondly, redundant contacts are included for enhanced reliability. Thirdly, special construction methods are employed to prevent accidental actuation or tampering. Fourthly, they demonstrate compliance with relevant safety standards, with IEC 60947.51 serving as an example for safety switches. In safety-critical applications, such as an e-stop circuit, it is vital to use safety-rated switches that meet the required performance level and hold certification from an accredited testing laboratory. The use of non-safety rated switches in safety applications can undermine the overall safety of the system, elevating the risk of injury or damage. Safety switches, designed for safeguarding personnel and equipment, play a crucial role in various industrial settings. These switches are specifically engineered to provide a reliable means of disconnecting power to machinery or equipment during hazardous situations. Understanding their functionality and the standards they adhere to is paramount for maintaining a safe working environment. Safety switches are not merely on-off switches, they incorporate features that ensure they perform reliably and predictably in safety-critical situations. One of the key features is positive opening operation, also known as positive break contacts. This means that the switch contacts are mechanically forced apart when the switch is opened, regardless of whether the contacts have become welded or stuck together due to wear, corrosion, or other factors. This positive opening action ensures that the circuit is reliably interrupted, preventing the machinery from continuing to operate and potentially causing harm. Redundancy is another important aspect of safety switches. Many safety switches incorporate multiple sets of contacts that are wired in series or parallel. This redundancy provides an extra layer of protection in case one set of contacts fails to operate correctly. If one set of contacts fails, the other set will still be able to interrupt the circuit, ensuring that the machinery is safely stopped. Safety switches are designed to be tamper-resistant, meaning that they are difficult to bypass or disable without proper authorization. This is important to prevent unauthorized personnel from tampering with the safety system and potentially compromising safety. Many safety switches are equipped with features such as shrouded actuators, locked covers, or password-protected settings to prevent tampering. Safety switches must comply with various safety standards to ensure that they meet specific performance requirements. These standards vary depending on the type of switch, the application, and the geographic region. One of the most widely recognized standards for safety switches is IEC 60947.51, which specifies the requirements for low-voltage switchgear and control gear. This standard covers various aspects of safety switches, including their construction, performance, and testing. In addition to IEC 60947.51, other relevant standards may include ISO 13849.1 for safety-related parts of control systems, and EN 60204.1 for electrical equipment of machines. These standards provide guidance on the design, implementation, and validation of safety systems that incorporate safety switches. The selection of safety switches depends on the specific application and the level of safety required. Factors to consider when selecting safety switches include the type of machinery or equipment being controlled, the potential hazards involved, the environmental conditions, and the applicable safety standards. For example, In applications where there is a risk of exposure to hazardous substances, safety switches with appropriate ingress protection rating should be selected. Similarly, in applications where there is a risk of mechanical damage, safety switches with robust enclosures and actuators should be chosen. Installation and maintenance are critical for ensuring the continued reliable operation of safety switches. Safety switches should be installed by qualified personnel in accordance with the manufacturer's instructions and applicable safety standards. Proper wiring, grounding, and mounting are essential for ensuring that the switches function correctly. Regular inspection and maintenance should be performed to identify any signs of wear, damage, or corrosion. Any defective or damaged switches should be replaced immediately to prevent compromising safety. Safety relays are electronic devices designed to monitor and control safety functions in industrial machinery and equipment. They play a crucial role in ensuring the safety of personnel and preventing accidents by providing a reliable means of detecting hazardous conditions and initiating appropriate safety responses. Understanding their functionality and applications is essential for anyone involved in industrial safety. Safety relays are not simply ordinary relays, they incorporate features that make them suitable for use in safety-critical applications. One of the key features of safety relays is their ability to monitor multiple safety inputs, such as emergency stop buttons, safety light curtains, and safety interlock switches. These inputs are connected to the safety relay, which continuously monitors their status. If any of the inputs indicate a hazardous condition, the safety relay will immediately de-energize its output circuits, shutting down the machinery or equipment and preventing further harm. Self-monitoring is another important aspect of safety relays. Safety relays are designed to continuously monitor their own internal circuitry for faults or malfunctions. If a fault is detected, the safety relay will immediately de-energize its output circuits and indicate the fault condition. This self-monitoring capability ensures that the safety relay is always functioning correctly and that it will respond appropriately in the event of a hazardous condition. Safety relays are designed to be fail-safe, meaning that they will always default to a safe state in the event of a failure. This is achieved through the use of redundant circuitry and self-monitoring functions. If a component within the safety relay fails, the relay will automatically de-energize its output circuits, shutting down the machinery or equipment and preventing further harm. Safety relays must comply with various safety standards to ensure that they meet specific performance requirements. These standards vary depending on the type of relay, the application, and the geographic region. One of the most widely recognized standards for safety relays is IEC 61508, which specifies the requirements for functional safety of electrical, electronic, and programmable electronic safety-related systems. This standard covers various aspects of safety relays, including their design, performance, and testing. In addition to IEC 61508, other relevant standards may include ISO 13849.1 for safety-related parts of control systems, and EN 62061 for safety of machinery electrical equipment. The selection of safety relays depends on the specific application and the level of safety required. Factors to consider when selecting safety relays include the type of machinery or equipment being controlled, the potential hazards involved, the number of safety inputs required, and the applicable safety standards. For example, in applications where there's a high risk of injury, safety relays with higher safety integrity levels, commonly referred to as SIL, should be selected. Similarly, in applications where there are multiple safety inputs, safety relays with multiple input channels should be chosen. Installation and maintenance are critical for ensuring the continued reliable operation of safety relays. Safety relays should be installed by qualified personnel in accordance with the manufacturer's instructions and applicable safety standards. Proper wiring, grounding, and mounting are essential for ensuring that the relays function correctly. Regular inspection and maintenance should be performed to identify any signs of wear, damage, or corrosion. Any defective or damaged relay should be replaced immediately to prevent compromising safety. Emergency stop, or e-stop, circuits are crucial safety mechanisms designed to quickly halt machinery or processes in the event of an emergency. These circuits are a fundamental component of workplace safety, providing a rapid means to prevent or mitigate potential harm to personnel or equipment. Understanding the design, function, and maintenance of e-stop circuits is essential for ensuring a safe working environment. The primary function of an e-stop circuit is to provide a readily accessible and reliable way to immediately stop a machine or process when a hazardous situation arises. This could include scenarios such as a machine malfunction, a worker becoming entangled, or any other situation that poses an immediate threat to safety. The e-stop circuit achieves this by cutting off the power supply to the machinery, bringing it to a safe and controlled stop. An e-stop circuit typically consists of several key components. Firstly, there are emergency stop buttons, which are strategically placed around the machinery or work area for easy access. These buttons are usually red in color and have a mushroom-shaped actuator for quick and intuitive operation. Secondly, safety relays are used to monitor the status of these stop buttons and to control the power supply to the machinery. Thirdly, contactors are used to switch the power supply to the machinery on and off. Finally, wiring and connections are used to connect the various components of the e-stop circuit together. The design of an e-stop circuit is critical to its effectiveness. The circuit must be designed to be fail-safe, meaning that it will always default to a safe state in the event of a failure. This is achieved through the use of redundant circuitry and self-monitoring functions. The circuit must also be designed to be tamper-resistant, meaning that it is difficult to bypass or disable without proper authorization. The placement of e-stop buttons is also an important consideration. Buttons should be located in easily accessible locations, such as near operator stations, pinch points, and other areas where hazards may be present. The buttons should be clearly labeled and easily distinguishable from other controls. Regular testing and maintenance are essential for ensuring the continued reliable operation of e-stop circuits. E-stop buttons should be tested regularly to ensure that they are functioning correctly and that they are easily accessible. The wiring and connections should be inspected for any signs of damage or corrosion. Safety relays and contactors should be tested to ensure that they are operating within the specified parameters. Any defective or damaged component should be replaced immediately to prevent compromising safety. E-stop circuits must comply with various safety standards to ensure that they meet specific performance requirements. These standards vary depending on the type of machinery or equipment being controlled, the potential hazards involved, and the geographic region. One of the most widely recognized standards for e-stop circuits is ISO 13850, which specifies the requirements for the design and function of emergency stop devices. This standard covers various aspects of e-stop circuits, including the placement of e-stop buttons, the performance of safety relays, and the testing and maintenance requirements. In addition to ISO 13850, other relevant standards may include IEC 60204.1 for electrical equipment of machines, and EN 418 for safety of machinery emergency stop equipment. These standards provide guidance on the design, implementation, and validation of e-stop circuits that meet specific safety requirements. The International Electrotechnical Commission (IC) plays a crucial role in setting standards that impact the safety and functionality of electrical and electronic equipment worldwide. Understanding the IEC and its standards is essential for engineers, manufacturers, and anyone involved in the design, installation, or maintenance of electrical systems. The IEC is a global organization that develops and publishes international standards for electrical, electronic, and related technologies. Its mission is to promote international cooperation on standardization in the fields of electrical engineering, electronics, and related technologies. The IEC standards cover a wide range of topics, including electrical safety, electromagnetic compatibility, performance, and environmental aspects. The IEC standards are developed by technical committees which are composed of experts from around the world. These committees work to develop standards that are technically sound, globally relevant, and widely accepted. The standards development process is open and transparent, allowing stakeholders from industry, government, and academia to participate. The IEC standards are used by manufacturers, regulators, and testing laboratories around the world. Manufacturers use IEC standards to design and produce safe and reliable products. Regulators use IEC standards to develop regulations and ensure compliance. Testing laboratories use IEC standards to test and certify products. The IEC standards are constantly evolving to keep pace with technological advancements and changing market needs. The IEC works closely with other international organizations, such as the International Organization for Standardization, ISO, and the Institute of Electrical and Electronics Engineers, IEE, to ensure that its standards are aligned with global best practices. The IEC standards cover a wide range of topics, including electrical safety, electromagnetic compatibility, performance, and environmental aspects. Some of the most widely used IEC standards include IEC 60364 for electrical installations of buildings, IEC 60947 for low-voltage switchgear and control gear, IEC 61000 for electromagnetic compatibility, and IEC 61508 for functional safety of electrical, electronic, and programmable electronic safety-related systems. These standards provide detailed requirements for the design, installation, testing, and maintenance of electrical and electronic equipment. They are essential for ensuring the safety and reliability of electrical systems in a wide range of applications. The NEC, National Electrical Code, and IEC standards, International Electrotechnical Commission standards, represent two distinct approaches to electrical safety and installation practices. While both aim to ensure safe electrical systems, they differ significantly in scope, application, and specific requirements. Understanding these differences is crucial for professionals working in the electrical field, especially when dealing with international projects or equipment. Firstly, let's consider the geographical scope. The NEC is primarily used in the United States and is tailored to the specific electrical practices and regulations within the country. In contrast, IEC standards are international and are adopted by many countries around the world, particularly in Europe and Asia. This means that equipment and installations designed to comply with IEC standards are often acceptable in a broader range of countries than those designed solely for NEC compliance. Secondly, we can consider the prescriptive versus performance-based approach. The NEC is known for its prescriptive approach, providing detailed instructions on how to perform electrical installations. It specifies precise requirements for wire sizes, conduit types, overcurrent protection, and other aspects of electrical work. IEC standards, on the other hand, tend to be more performance-based. They set out the desired outcomes or performance criteria that electrical systems must meet, but they provide more flexibility in how those outcomes are achieved. This allows for innovation and the use of different technologies as long as the required safety and performance levels are met. Thirdly, there is the voltage and frequency considerations. The NEC is based on a 120/240 volt system at 60 Hz, which is standard in the United States. IEC standards accommodate a wider range of voltages and frequencies, reflecting the diverse electrical systems used around the world. For example, many countries that use IEC standards operate on a 230 volt system at 50 Hz. Therefore, equipment designed for use in these countries must be compatible with these different electrical parameters. Fourthly, wiring methods and materials come into play. The NEC specifies particular wiring methods and materials that are approved for use in the United States. These requirements are based on the specific environmental conditions and building practices prevalent in the country. IEC standards allow for a broader range of wiring methods and materials, as long as they meet the required safety and performance standards. This allows for greater flexibility in selecting materials that are appropriate for the specific application and environment. Fifthly, equipment and product standards must be considered. The NEC references Underwriters Laboratories, commonly referred to as UL, standards for the testing and certification of electrical equipment and product. UL is a well-known organization that provides safety testing and certification services in the United States. IEC standards, on the other hand, reference various international standards for equipment and product testing. This means that equipment and products that are compliant with IEC standards may not necessarily be compliant with UL standards, and vice versa. Finally, the updating and revision processes differ. The NEC is updated every 3 years by the National Fire Protection Association, commonly referred to as NFPA, through a consensus-based process. This process involves input from a wide range of stakeholders, including electrical contractors, engineers, manufacturers, and regulatory agencies. IEC standards are updated on a regular basis by technical committees, which are composed of experts from around the world. This process also involves input from various stakeholders, but it is often more focused on technical considerations than the NEC updating process.